Hello and welcome to another class of ATMO 412. Today we will continue talking about extratropical cyclones, and after having discussed some of the early research that went into them and how that was naturally interlinked with the birth of modern meteorology, today we want to get a little bit into the sort of the nitty-gritty and the physics of these systems, and particularly we're interested in learning how these systems are born, okay? And this process is a process that is known as cyclogenesis. And there are many ways of approaching the question of cyclogenesis. The first way that we want to approach, that we want to use to approach this is to consider simply vorticity. And vorticity is an obvious candidate to look at cyclones because by definition, cyclones are things that turn. And what better than vorticity to look at these things? And we are going to consider absolute vorticity. And if we consider this equation over here, absolute vorticity is a variable that describes cyclones perfectly, and these are typically associated with maxima of absolute vorticity. The evolution of absolute vorticity is dictated by a variety of components. There's certainly an effective component over here, there's a tilting component, there's a stretching term, and there's friction. Okay. Now, we could imagine a simple situation where we could ignore friction and we could say, let's just ignore any tilting. So let's assume that the vorticity is already vertical. Okay, there's nothing to tilt back. And this effective term, these two, we could put them back into the time derivative and turn this into a Lagrangian derivative. Well, if we do that, then we would end up with a very, very simple equation that only depends on the stretching term. Okay, if there's no friction, if there's no tilting, then the only thing that can affect vorticity is the stretching. And we could think of this hypothetical situation where we have some kind of a prefrontal zone, frontal zone over here, and maybe this is a stationary front, so it's not going anywhere. There are two different air masses that are moving at opposite velocities, and this would be a natural region to create vorticity because of shear instabilities that might be formed along the front here. And let's assume that there's some kind of a upper trough that is advancing. So here there would be some kind of a vorticity advection, and if you remember, vorticity advection is associated with ascending motion, and whenever this approaches over here, then this causes a stretching term to be non-zero. And particularly if we consider the mass continuity equation, we can always rewrite that term as a convergence of horizontal velocities. And this is what the equation looks like. And this, notice the Lagrangian derivative over here. This tells you that if this convergence remains constant, then this, if you have divergence aloft and that is constant, then this is essentially the equation of an exponential. Okay, so in case of a constant divergence, okay, so this is negative is plus. This is an explosive growth of vorticity, okay? Normally, this doesn't really happen in nature. It doesn't just keep exploding, obviously. It doesn't keep growing because friction would at some point intervene and act to moderate. But, to first degree, this is a good way to understand what is happening. And it also suggests that if we have some kind of pre-existing vorticity, then this is something that we need to keep an eye on, particularly when there's the interaction between troughs and fronts. It's always something that leads to the generation of vorticity. Not the generation, but the exponential growth of vorticity. And notice that this term is not particularly, this mechanism is not particularly effective for anticyclones, because for anticyclones, the relative vorticity and the planetary vorticity have opposing signs. And so in that case, it's not good. And so we can see an example here, for example, where we have this low pressure system, this cyclone essentially, that is advancing to the right. And here we have a high pressure system to the north. And this causes some ridging over here. And notice that the low collides with this ridging. Now, what ends up happening is that this high doesn't grow exponentially. It doesn't become like an exponentially strong high pressure system, but the mechanisms that led to the increase of the vorticity here will lead to the growth of vorticity east of this ridge. And so it kind of looks like this low is tunneling. And so now we start to notice as this low over here sort of starts to disappear, the new low is formed over here and is strengthened. And so it keeps growing. So you see that the high hasn't really changed much, but the low over here has been able to grow. So it's like anticyclogenesis is not, the tilting term is not as strong or as effective as it is for cyclones. The other perspective here is that of the pressure view. And pressure is, in a sense, important because what we were just talking about, we have a stretching term, and the stretching term works if there's some kind of divergence aloft. And this divergence means that there's some mass that is taken out, that is taken out of the column, okay? But because the atmosphere is in a state of hydrostatic equilibrium, whenever we talk about low pressure systems and divergences, these things are, in a sense, interrelated, right? Because these correspond, if you have a low, then it means that something must have been exporting air out. And so the air pressure and the divergence properties are interrelated. So pressure is also another natural variable to consider these processes and to consider cyclogenesis. And here it's relevant because, what we want to consider here is that when we consider the jet, and we consider in this case simple wave pattern in the upper levels, and this is, the black lines are schematic representations of 500 hectopascals geopotential height. And because in the troughs and in the ridges, centrifugal and pressure force are oriented in opposing sense, okay, so for example in the flow, centrifugal and pressure force are in the same direction. So this causes the flow over here on the ridge to be super geostrophic, and so in turn this causes a convergence here from going from the ridge into the trough and a divergence over here. And so the divergence is because pressure is a measure of the weight of the air column, and because the atmosphere is in a state of hydrostatic equilibrium, the divergence is going to be associated with the formation of a low at the surface in this column, and the low will be then associated with some cyclonic vorticity, and together with the stretching term, this could cause the growth of the cyclone, okay? So pressure and vorticity are different ways of looking at this process that is really just the same process, essentially. And this is also a nice way of looking at this problem because it ties together the jet stream and the cyclogenesis problem. And of course, these two these two perspectives can also come together into the QG framework, where things can be sort of related. And the QG framework is not great necessarily to look at the explosive cyclogenesis, because the tilting term is really just a fixed F0, so it's just a fixed term, and it's not like in the equation that we saw for the vorticity. But when we consider the high tendency equation is something that can be useful to explain the formation, the cyclogenesis. And in particular, when we talked about the high tendency equation, we saw that both warm advection, the increase of warm advection with height, and cyclonic vorticity advection, they were forcing mechanisms associated with fall of geopotential heights, which again, we could see as the arrival of the trough, or the digging of the trough in some cases, which can then be related to cyclogenesis. And in fact, surface low pressure systems very often track toward regions of really strong low tropospheric advection. And so these perspectives are all kind of complementary, if you will. One thing that I also wanted to mention here, since we were talking about digging and lifting troughs and ridges are characterized by a certain amplitude, obviously, and different systems of different amplitudes. Because these amplitudes are also characterized by different forcings, it's clear that smaller wavelengths, meaning higher frequencies in the flow, are associated with greater values of cyclonic vorticity advection. And so for equal amplitude of the waves, shorter wavelengths can be important in generating stronger ascent, so in facilitating cyclogenesis even more. Okay, so sometimes the arrival of a short trough, of a short wave on a big trough, can lead to an enhancement of cyclogenesis. Okay, so we talked about the upper levels until now. The lower levels are not mere spectator into this process, okay? And one way to see it is if we consider the tendency equation for the thickness of the atmosphere. And the thickness, we saw at the beginning of this course, was the layer average virtual temperature. Let's pretend it's temperature for now, just to simplify our lives. And if you do all the calculations, then you can arrive to an equation that looks like this. The square brackets are an average over a certain layer of the atmosphere. This is the adiabatic lapse rate. It can be dry or moist. And this is the environmental lapse rate. Okay, so we have the advective term. This is simply term that is proportional to the lapse rate. And in a sense, this is the vertical advection term, if you will. And this is the diabatic term. Okay. Now, we can use the thermal wind equation to show the importance of the low-level winds, okay? And in particular, the thermal wind is simply defined as the difference between the geostrophic wind at some height and the geostrophic wind at 1,000, at the surface. Let's assume that it's 1,000 hectopascals, just for simplicity. Now, because the thermal wind is parallel to the height contours, it doesn't really contribute to thermal advection, which means that we can always rewrite the temperature equation in this form. Okay? So this is essentially showing that in this case, it's the behavior of the thickness of the atmosphere is controlled by the geostrophic advection at 1,000 hectopascals, so near the surface. Okay. Okay. Now, why is this relevant, or how can this be relevant? Well, we can consider a case in which we have a situation near a developing cyclone, and we have a surface low over here. These dashed lines are 500 millibar geopotential heights. This blue over here is a cold front, and this over here is a warm front, okay? So there's cold air over here, warm air over here. And obviously, the winds are causing warm advection over here and a cold advection over here. But this term that we just talked about here is interesting because this will lead to cold advection to the west and to warm advection to the east. Okay, and so this will cause an expansion of the ridge even more, and a digging of the trough even more, because it's going to shrink. Cold advection is going to shrink the column, so this trough is going to come down even more, and so this creates almost like kind of like a feedback, if you will, between the advection and the thickness. Okay, and this is another way of seeing it, where we're just looking at this AB cross section over here, and this is a AB cross section. This is a function of height, and warm advection here to the south, again driven by 1000 hectopascal, is causing a thickening of the column, and here it's causing a decrease in the thickness of the column. So we have cold advection on this side, and this causes an even stronger upper level trough. This causes, if you will, more stretching, so this intensifies. This causes stronger warm advection, stronger cold advection, and it keeps going like this. Okay, and sort of this inflection point, tends to be sort of aligned with the surface cyclone, which leads to sort of the maximizing for ascent over here, which then leads to a greater vortex stretching. So as I was saying earlier, sort of almost like a positive feedback. Okay, and we'll talk about baroclinic instability, but this is sort of a consistent picture with baroclinic instability. Now, this term, the vertical term, often called the breaking term, can come to oppose the feedback, because in a little typo. I'm an ESL, so anyway, well, apologies for the typo. But in the zone of where we have warm advection, then in that case we typically have ascent, and so in this case, this term is all negative. Okay, so omega is negative. This is typically positive. Okay, because the adiabatic lapse rate, or the environmental lapse rate, is usually sub-adiabatic. So this is usually a positive term, and so this will be negative. So this is a negative term, and in the zone of cold advection, on the other hand, we have the reverse situation where we have omega that is now positive, and so this is the opposite sign of this term over here, and so it kind of breaks this explosive growth, unless of course the environmental lapse rate is really close to the adiabatic lapse rate, in which case this term is almost insignificant. But otherwise, this will typically something where, like the explosive cyclogenesis, the feedback mechanism is usually killed. And as I said, it makes a difference whether we are in a saturated environment, and so then we have like moist adiabatic growth, or we are in some kind of an unsaturated case. And this is an example, just a simple schematic of this mechanism. This is sometimes known as the Sutcliffe-Peterson self-development. Okay, we can see we have some temperature advection, and so we have temperature advection, boundary layer heat, and moisture fluxes, and latent heat release. They all contribute to the amplification of the upper wave, and also, importantly, reduce the wavelength between the trough and the ridge that we see downstream over here. So this is obviously going to lead to greater ascent, greater upper level divergence, and strengthening of the cycle. Okay, there is another way of looking at sort of another framework, if you will, to look at these at this growth and the development of cyclones, and this is with the PV framework that we discussed. So we've already talked about the vorticity framework. PV is similar but different, and we talked about PV as, this great variable that is conserved in many cases, and we can also use it to represent the growth of cyclones. Okay, and this represents a simple case where we have this figure over here. Here we have the red lines represent isotropes, as always, and we're thinking about surface level positive vorticity, positive PV, and this is related to some surface warm potential temperature anomaly. And notice that this causes a tilting of the isotropes over here, and it causes cyclonic vorticity. Cyclonic PV causes a region of cyclonic PV over here. Okay. And PV is useful because, apart from all the conservation properties of PV, it is, it packs a lot of information, and because the interactions that happen also affect the stability of the atmosphere, and this is something that we would be able to capture with PV. One of the things that we observe often when we see these cyclones is that we observe the development of pretty significant positive PV values. Not the development, but we observe pretty significant PV values in the mid-troposphere, so in the much lower levels. We know that these exist in the stratosphere, but often we observe that they descend all the way down. And these are very often caused by upper level frontal systems that essentially cause the descent of stratospheric air, essentially coming all the way down. These systems can distort the stratosphere and cause these injections of high PV air into the troposphere. And here we can see sort of a schematic of the different regions of PV that we observe in a cyclone. This is the low-level low that is associated with the cyclone, the warm front, which is characteristic of the cyclone, and the cold front over here. And here we have different regions of various levels of PV. So first of all, over here, because of the warm advection, we have a warm anomaly, and warm anomalies, as we saw earlier, cause the formation of PV values. Okay, so that's sort of by a diabatic heating almost from the surface fluxes. And we also have stratospheric air that is coming in from here that is being brought down here. So we have pretty significant PV values. But then we also have maxima in the lower troposphere that are caused by typically latent heat release. So these tend to be fairly cloudy regions right behind the cold front. And finally, over here, where there's sort of an upper ridge to the northeast of the cyclone, we typically have negative PV anomalies. Okay, and these are typically associated with diabatic processes that happen over there. Okay, and so in a way, the cyclogenesis, in a sense, could be considered as the interaction, or as a result of the interaction of these four different kinds of PV anomalies that we observe. Why do we have these different anomalies, or what causes these anomalies to amplify? Well, it's a combination of things, but typically it's a mutual amplification, and diabatic processes also help. So let's start with the mutual amplification, and this is something similar to the Sutcliffe-Patterson or complementary perspective, right? And this involves a positive feedback, essentially, between an upper level low and between the upper levels and in the lower levels. When we discussed the Sutcliffe-Patterson feedback, we were considering a cyclone in the lower troposphere and an upper level wave that was passing by. Okay, so something similar happens here because and it's something that we could see using the inversion technique, but we could start by considering an upper level PV maximum over here, and this is typically associated with this cold trough, okay, and a cyclonic circulation, okay. Now, typically, assuming that the static stability is not so strong, this trough will extend pretty low in the troposphere, potentially even going all the way to the surface. If we assume that there's a normal meridional temperature gradient, as we would expect near a jet stream, then in this case we would expect some cold advection coming down all the way down over here. Okay. However, this cyclonic vorticity over here will likely cause warm advection over here. Okay, there also might be sort of some pre-existing lower anomaly. Okay, so if we move then to the surface and we consider some kind of warm anomaly, then warm anomaly would have some kind of a cyclonic circulation that is again represented by these vectors over here. Again, let's assume that the static stability is not so strong. This will extend all the way up. And if it extends all the way up, then the cyclonic motion associated with this will cause an intensification of the cold advection over here. So a deepening of the trough, in a sense, over here. And so you can see how this is now going to lead to a positive feedback, because this is going to intensify, so this causes a stronger warm advection here, and it starts to feed back. Okay, so in a way, this is maybe another way of considering the self amplification mechanism that we saw with the Sutcliffe-Patterson Shockley-Patterson mechanism. And because these different anomalies have different ways, different motions, different propagating speeds, it might be that these two will get lost and we'll lose touch with each other. But because the wind speeds are also different, it so happens that these two anomalies will move at roughly similar speeds, and so this causes this system that is self-developing to move all at the same speed. One important thing also is that these two should be not exactly stacked on top of each other, but if they're slightly offset, then this really helps in favor of this. And of course, there can also be some kind of a PV redistribution, either with precipitation or with latent heat release. And we're not going to get super deep into it, but diabatic heating also plays a role. And here, this is various terms that contribute to the PV features and of a cyclone. And this is a famous cyclone. This is a President's Day cyclone of 1979. And this is a simulation that was done with WRF, the Weather Research and Forecasting Model, for February 1979. And this panel over here shows wind and pressure on the dynamic tropopause. Okay, so notice that there's this cyclonic motion over here. And then this over here, we have wind and potential temperature on the dynamic tropopause. Okay, so over here. And then we have layer average wind and PV in the 800 to 700 hectopascal layer. And finally, sea level pressure over here with temperature anomaly. Okay, so this is showing very nicely the worm anomaly term over here. You can see it pretty nicely over here. It turns out that, well, in our discussion, it is pretty clear that the existence of troughs is pretty crucial to explain the formation and the intensification of cyclones. But where are troughs coming from? And what leads to the formation of these troughs? And believe it or not, this is not a question that this is a question that has been looked at only very recently. And to our understanding, so one of the first people who looked into this was Sanders, who in 1988 did some climatology of these troughs and found that topography really does potentially play an important role. And the author found that there were a number of upper troughs genesis events over North America, for example, and we observed some also over here near the Tibetan Plateau, and it's kind of hard to appreciate, but this is sort of a northeast Europe, really north east of Europe. So this is just to give you an idea of where those could be. And another important thing that we need to keep in mind is that when we talk about moisture is an important component of atmospheric dynamics really, but of these cyclones as well. And there are many cases, like the one represented here, where there are systems that advect a lot of moisture out of the tropics, okay? And these are plumes of moisture that is sort of taken from the tropics and brought towards higher latitudes. And these are really, really important in the transport of moisture on the planet. This is an example that I'm showing here from 1986, and this is showing the west coast of the United States. These have different names, and recently I think atmospheric rivers is the name that is favored and that is used in more contexts. But here in Hawaii, we often call it the Pineapple Express. It's something that starts from roughly Hawaii and brings moisture to the American continent. And often these cause like some positive, they can certainly lead to an intensification of the cyclone, and there's almost like a positive feedback in the sense that when there's advection of these plumes, the latent heat release leads to PD anomalies in the low troposphere, which then forms a low-level jet that exports even more moisture from the tropics. This is another couple of pictures that I wanted to show. The top is low tropospheric water vapor during a flooding event in Tennessee in 2010. That is a depiction from GOES 13. That is water vapor, and we're overlaying 700 hectopascals mixing ratio analyzed with GFS, and on the bottom, this is the same event, but it's showing mixing ratio shaded at 850 hectopascals. We have 850 hectopascals wind barbs, and the contours are 900, 700 layer PV. So this is another, you can see this plume of water vapor that is just coming out of the tropics here in the Caribbeans, going all the way up to the American continent. This is a bit of it's a bit of a popular topic, I guess. Sometimes people talk about bomb cyclones, explosive cyclones. This is nothing other than saying that there was a cyclone that developed really fast. And there's a way to make this quantitative, and if a cyclone, the sea level pressure inside of a cyclone decreases by more than 24 millibar over 24 hour, weighted by the latitude where we are. This is a unit of measurement called a bergeron, and if the cyclone exceeds 1 bergeron, then we say that this is an explosive cyclone. We talk about explosive cyclogenesis. These are contours that denote areas of explosive cyclogenesis. It's not too surprising that they're here because this is where the storm track is. I wouldn't say that there's anything particularly deep about explosive cyclones, but if your uncle asks you about bomb cyclones, now you can tell them, you can give them the difference. And obviously the maritime locations are kind of favored because they have a pretty warm boundary layer. Which can lead to transfer of heat and moisture, and can precondition the atmosphere before a cyclone event arrives, and so it sort of increases the baroclinicity of the area, and it can also reduce the static stability, which facilitates the self-development feedbacks that we talked about. Over the ocean, you have no mountains, and so there's less friction that are pretty important. This is a very dated depiction of what cyclogenesis might look like. This is the East Coast, I believe. And finally, just keep in mind, just note that there are ways to classify cyclones. And we talk about type A cyclones when they are formed simultaneously at all the levels without a clearly defined upper trough. And we talk about type B cyclones that form when we have these upper troughs that overtake the frontal zones that we talked about earlier. I think this is all I had to say about cyclones. Next, we will talk about fronts, which are very much a component of cyclones and a very important one. Thank you very much for listening.